So, in the last class, we have started the quantum mechanics and its basics. We have seen that where in which fields classical mechanics fails, and we have a new branch of physics, that is quantum mechanics. Now, we will see some important phenomena in some of the upcoming lectures, and in this lecture, we will see the black body radiation, and then we'll see the about the Planck's rules, and then photoelectric effect. So first we will start from electromagnetic induction. So what is electromagnetic induction? We know about the electromagnetic waves. The range of wavelengths of frequencies over which the electromagnetic radiation extends is known as electromagnetic spectrum, in which the number of electromagnetic radiations are distributed over their increasing or decreasing number of their wavelength or frequency. So in order of wavelength in the electromagnetic spectrum as follow. So if we see, there are two ways. There in the left side we have frequencies decreases from top to bottom, and here frequencies decreases, and in the right side the wavelength of the electromagnetic waves are decreases from uh, bottom to top. So arrow sign shows that the frequency is decreases from top to bottom, and here the wavelength is decreases from bottom to top. So if we see that the gamma rays has much more frequency, then X-rays has lesser frequency. There's gamma rays, ultraviolet, then visible, infrared, microwave, and radio wave. Radio wave has the very less frequency compared to other frequency electromagnetic waves. And the same case, as we know that wavelength is inversely proportional to frequency, that is here lambda is inversely proportional to frequency, or we can say frequency is inversely proportional to lambda. So therefore wavelength is decreases here, and wavelength decreases from radio wave to gamma wave, reverse process. The order of wavelength and frequency difference wave electromagnetic is shown is above. The wavelength in the range of, here the range, 4000 angstrom to 7000 angstrom. We know that the angstrom means 1 angstrom is equal to 10 to the power minus 10 meter. This is the range of denomination of angstrom. So 4000 angstrom to 7500 angstrom lies in the visible region of the electromagnetic spectrum with respect to the human eyes. This is the range where we see all the objects in this region. So here the uh, pictorial representation of the range of electromagnetic waves. They are shorter waves, so gamma rays has the shorter wave, while the radio wave has the high wavelength, or it has the low frequencies. Now, uh, electromagnetic spectrum wave theory could not explain the following phenomena, that is black body radiation, photoelectric effect, variation of heat capacity of solids and temperature, and line spectrum of hydrogen. So first we will see the black body radiation, that is idealized system. So first introduced by Gusten Kirchhoff in 1860, a black body is theorized physical object which is mass and that can be internally absorb all energy target. Means if there is a black body or something like a body, if the incident light is falls on it, it absorbed everything and reflect nothing. So R is equal to 0. Here R is equal to 0. And containing it wholly and not reflecting of any residue. Independent of the wavelength of the incident radiation of the angle of incident, it is called, and when body, this phenomenon is called black body radiation, and this body is called black body because it absorbs all lights that falls on the surface. A black body at a constant temperature, a black body at a constant temperature and therefore in thermal equilibrium radiates electromagnetic black body radiation. That means if this is a body, black body, after absorbing everything, all radiation, after some times it's start radiating, and this radiation is called black body radiation. The emitted radiation is according with the Planck's law, which H Planck's law, that means E is directly proportional to frequency. That means the energy of this radiation is directly proportional to frequency. So according to our Planck's law, we know that if we remove the proportionality constant, we have a constant. This is called Planck's constant, which has the value 6.634 into 10 to the power minus 34, meaning that the emitted radiation has a spectrum that is purely dependent on the temperature of the black body, not the shape and composition of the body, black body. A black body at a constant temperature has two desirable properties: that it has an ideal emitter, that means it's emit everything, no reflection, no absorption. The thermal radiative energy emitted by the black body is as much more than any other body at the same temperature. It is diffuse emitter, that is the energy which is measured per unit area perpendicular to the direction of the black body radiated isotropically independent of the direction. That means it does not depend upon the direction. Black body is one that allow all incident and all type of radiation from the direction and internally absorb all of it. So we conclude that black body has the zero reflectance and zero transmittance. That means R, if R is the reflectance, so R is equal to 0, and T is the transmittance, then T is equal to 0. So any real body also absorb radiation which is very lower than black body. Example of black body is, very much example is lamp black and the platinum black. Now there are some laws which are introduced later by some scientists, in which we have Wien's law. It is also known Wien's displacement law. This is also called Wien displacement law. So what is Wien displacement law? It is the relationship between the temperature of the black body, that is an ideal substance that is emit absorb all frequency of light, and the wavelength emitted, the maximum intensity at the temperature. So this law says that the exact frequency distribution of emitted radiation from a black body depends only on its temperature. Wiens found that the radiated energy, that is dW per wavelength interval d lambda, has a maximum at a certain wavelength. Maximum, we have lambda m for maximum, and maximum shift for shorter wavelength as a temperature T is increased. He found that this T lambda m T is an absolute constant. He found that means lambda m into T is a constant quantity. That means lambda m is inversely proportional to T, or we can say that T is inversely proportional to 1 by m lambda. So lambda into t. So we can see lambda into t is equal to constant, at least this constant is replaced by b. So we can write it as lambda m uh, is equal to b by t. Here this is the equation where b is the Wien's displacement constant, whose value is calculated by 2.897 10 to the power minus 3 m into k. So this is the um, wavelength of intensity relation curve. In the graph, there is a peak intensity, but the Rayleigh Deslegends, a mathematical formula of waves there are, must be an infinite peak as it approaches zero wavelength. As we move to the zero, the peak of the graph move towards the infinite value. So the wave theory failed to explain this experimental graph. Later, Planck's equation, which considered the atoms and molecules could emit or absorb energy only in a discrete quantity known as quantum and not the continuous manner. Quantum means discrete, not continuous. So tail with the graph providing the particular nature of the light, that is the quantum nature of the light. Next is the Stephen's law. Stephen Boltzmann, both scientists, law established the total amount of radiation energy produced by the black body per unit from a specific area A at absolute temperature is directly proportional to the fourth power of the black body. Fourth power of temperature of black body. Sorry, temperature of property. That means uh, mu, that is if mu is the energy radiated per unit time of a specific area, that is it is directly proportional to area as well as the fourth power of the temperature. If proportionality sign is removed, therefore this mu, that is energy, is equal to sigma, which is the proportionality constant a and to t to the power 4. This sigma is called um, Stephen Boltzmann constant, whose value is 5.6 into 10 to the power minus 8. This is the unit. And it is proper constant, and T is the temperature of the black body. For a body that is not black, radiation emission is given by U is equal to epsilon A T to the power 4. U is equal to, we can say U or mu, but most of the cases it is written as, some of the cases it is written as U. So we will also use that as U. So this is energy is denoted by U. So we can write it as U. And here for a black body, when a body which is not a black body, the radiant emitted energy is given by another formula, that is U is equal to epsilon A T to the power 4, where epsilon is the emissivity, which is defined as the ability of a surface to radiate energy in the form of thermal radiation. These are the some derivations for the black body radiations, in which we have seen that the spectrum of the body and what are the relationship of the energy with the frequency and the wavelength. That's it for this class. In the next class we will see about the famous photoelectric effect and its properties. uh, what is the photoelectric effect, what is it is used in quantum mechanics in the later classes, in the higher classes or advanced quantum mechanics. So hopefully you have enjoyed this class. So we will see you in the next lecture, that is of quantum mechanics.